Okay, good afternoon, everyone. Very big welcome to this RISCAuthority webinar on the subject of Watermist and why it's complicated. For those of you not familiar with these webinars, we run a series. We try to hold one every month on topical issues, some of them close to the insurer membership of RISCAuthority, but others like this one open to all comers because being much of a common interest. Clearly, this has been a very popular subject title where we've had a record number of subscriptions to this webinars, and I can see a counter increasing all the time in front of me of the number of people listening in. So thank you very much for taking the time. Now, the webinar itself is accredited by the Chartered Insurance Institute, so you can claim your CPD points after it. If you need a certificate, please don't hesitate to get in touch and request one, but I think they do actually take it on trust. I should also add that this webinar will be recorded. It is fairly fast and furious in the rate of delivery, I'm afraid, because it is quite a complicated subject, but the slides will be downloadable for you to refer to if anything's not clear. And of course, you're also welcome to get in touch with us afterwards for further clarification. So probably worth commenting, I'm Dr. Jim Glockling, Technical Director of the Fire Protection Association and Director of Risk-Authority. And I suppose it's probably worth just going through with what authority I suppose I speak on this subject. Really, I suppose it started, I did a postdoctorate in Watermist suppression of electrical protection on behalf of insurers in 1996. We undertook many Halon replacement studies, of which Watermist certainly featured large. And since that time, we've done many replacement studies for the Ministry of Defence, generally for warship and submarine protection, and culminating in authorship of various defence standards for Watermist systems, which are now on the new platforms, Type 26, the Queen Elizabeth aircraft carriers and the like. And probably most pertinent to what we're talking about today is we also conduct an awful lot of forensic investigations where we see suppression systems fail. So we do have quite a good understanding of how they perform and what the common challenges are. Now, as I said before, it's a difficult subject to compress into just 40 minutes. I'll do my best, but inherently in that I will be making some quite gross generalizations and simplifications, so I apologize for those now. If I had to caveat everything I said, we'd be here for a number of days, I would guess. The other thing to probably be aware of is that not everyone listening to me will agree with what I've got to say. It's the nature of the subject, and people hold some quite strong views in these areas. Looking at the audience that has subscribed to this, in the audience, I know we have all ranges of capabilities. We have experts who could perfectly well be delivering this, so welcome to them. But an awful lot of end users as well, really just seeking guidance and clarification for their own purposes. Those who know RISCAuthority will obviously, we have a declared bias in terms of business and property protection. In that we seek resilient systems, things which are dependable, since they underpin insuring. Right, so without further ado, the learning objectives, requirement for the certification. We're going to go through what is Watermist, why it's different to other forms of suppression, and I hope if you take nothing away from this, it'll be that it really is different in the way that it operates, and that really underpins why it will always be complicated to specify and to prove. Also, the importance of establishing exactly what protection objectives are, operational dependencies with other systems, and how your selection might be influenced by whether you're looking for life safety, property protection, or some other remit to fulfill. So often we see this being left out. People put in a suppression system or an extinguishing system without actually really thinking about what needs to be left should it ever be required in anger. We also need to address the issue of equivalency, and this is because when we look at our building regulations and how some suppression systems are referenced, often they will cite sprinkler systems and ask for equivalency if a different type of system is to be used. And that's very important, specifically for those who are protecting the built environment and particularly for life safety objectives. Now, risk authorities put in a lot of work trying to clarify the situation for people. I'll go into that, and also provide some basic rules of thumb. Now, these are really things which people may disagree with, but we found that they hold true when trying to specify good systems. So I'm not going to go into the details of this, but what is Watermist? Essentially, it differs from things like sprinkler systems because the water droplets are very finely divided to be much smaller. And in doing so, that gives them an amazing surface area for the exchange of heat and mass over. So if you want to change a lot of water into steam very quickly, the first thing you do is to cut it up as fine as possible and make it available for boiling off. And this is the difference between really a Watermist system and a sprinkler system. In order to achieve this very fine subdivision of particles, generally these systems might operate at much higher pressures than other traditional water systems, and for this we might use compressed gas or high pressure pumps. The mode of operation is generally described as a part thermodynamic cooling of gases during the evaporation process of water into steam, and oxygen reduction as this steam displaces oxygen from the compartment. But many other factors will also come into play, and really that I'll show you in probably more detail than is healthy during the course of this talk. These systems can be implemented in a number of forms. Traditionally, they've been what we call deluge systems, where the heads will not have a sprinkler bulb in them, or will not have a glass frangible bulb in them, but will actuate on an open pipe system when the pump is switched on. And these can be operated on a compartment or local application protection. But increasingly, we're seeing systems which are bulb actuated. And we've got some rather strong feelings on some implementations of those, which we don't feel might be appropriate. But more on that later. So, first of all, why is Watermist different? I do apologise for putting up a picture of the fire triangle. Nearly every talk on fire starts with it. But I'll be as succinct as I can. But we all know that fires require heat, oxygen, and fuel to sustain combustion. And so any suppression system that comes to the fore is going to act on one of those. But it's actually a little bit more complicated than that, because we also do need to consider the chemistry of combustion also. So you may be more familiar with the fire tetrahedron. And really this is about interrupting the chemistry of the combustion process itself. So whilst we might be used to our O-level chemistry telling us that hydrogen and oxygen mix to make water in a simple equation, in actual fact, it takes place as a series of steps where bonds are broken and remade between the various compounds that are involved. And while they are in this heightened state of being split up, they form free radicals. And in suppression terms, there is an opportunity for other molecules to be introduced, sort of to steal these, so the chemistry of combustion can't complete. And this is probably most familiar action that we'll move on to think about of some of the gases which have historically been used for looking at fire. So we can really address fire by tackling limiting it of oxygen, limiting it of heat or fuel, or interrupting the chemistry of combustion itself. Now, I thought it might help to understand how Watermist works by first of all looking at other suppression systems very quickly, with the popular ones being sprinklers, inert gas systems and CO2 systems, chemical gaseous agents, and the traditionally used gases such as Halon 1301, and may help us understand a little bit how Watermist works in its own right. So, looking at sprinkler systems, often people are slightly confused about how sprinkler systems work. We're very used to thinking we put water on fire and the fire goes out. But actually, when it comes to things like sprinkler systems, generally they are fuel removal systems. And generally what they achieve is making stuff that would normally burn, not burn. So in the case of solid fuels like cardboard, dry cardboard is a fuel, wet cardboard isn't. And a lot of sprinkler protection is about pre-wetting the fuel that could soon become involved in a fire. And that determines how water is discharged from them. Now, if you're protecting some liquid fuels even, this can still apply. Alcohols with water, at a certain percentage, they will burn, and below a certain amount of dilution, they will cease to be able to be combustible. So dilution of alcohol fuels to the point where they become non-combustible still classifies as foam removal. And for other types of Class B fluids like petrol and diesel, again, additional chemicals can be added to the water entering the sprinkler system, such as firefighting foams, which essentially will render the fuels non-combustible or separate them from further participation in the fire by a physical barrier or a skin or a frothy layer, if you like. Now, obviously, they do remove heat as well from the seat of the fire directly, but really it's common practice that for sprinklers, the area will burn out where the fire initiates because you've made the surrounding product non-combustible by the flow of water over it or the absorption of water into it. But we need to be clear about our terminology with all systems as to whether they constitute suppression systems or extinguishing systems. There's a lot of confusion over the word suppression. Sometimes it's used interchangeably with the word extinguishing system as well. But for the sake of this talk, let's be clear. Suppression means that the fire isn't assumed to go out. It is meant to be constrained and held to a size, but then there will need to be a third-party activity to come and finish the job off, which commonly for sprinkler systems will be the fire and rescue services, in that the sprinkler system in actuating will have made the building structurally safe, constrained the fire to a manageable size so that it is still appropriate for approach by the fire service with their type of equipment and PPE. Now, the design criteria for sprinkler systems is a very simple one. Essentially, at the end of the day, for a particular type of storage arrangement and ceiling height, it gets described as millimeters of water landing on the ground per square meter, a very simple design criteria. If we look at the equivalent for gaseous systems or inert gas type systems, these are oxygen removal type systems, where the inert gas displaces around 40% of the enclosure's volume, leaving a residual oxygen concentration that doesn't sustain combustion. And for typical sorts of fuels, that will be somewhere around 12% of oxygen and below. There is some slight variation in the performance of the different gas mixtures, because when you introduce additional quantities or when you change the makeup of air, it transports heat differently. So there are some differences in performance between the inert gases, but they are very minor. Gaseous systems can't really be suppression systems. They need to extinguish the fire in order to fulfill their remit. And for that, obviously inherent in the design will be precise control over the environment in which they operate. So we need to ensure that the compartment is sealed so the gas doesn't just dissipate out. We need to ensure that at the time of discharging the gas, we don't destroy the enclosure. When you inject these gases, if 40% of the compartment's volume needs to exit, it needs to do that in a means which is controlled to an appropriate location and doesn't raise pressures inappropriately. And then having discharged it, there needs to be mechanisms to seal the enclosure and ensure that you can hold on to that gas quantity. At the end of the day, these are quite highly developed systems. Again, the design criteria are very simple. For any given compartment volume and type of fuel and compartment air tightness, it looks at just the amount of gas required to achieve a residual oxygen concentration, which is appropriate to the fuel being protected. So very straightforward. A little more complex with gaseous, chemical gaseous systems. So these are, if you like, gases which are almost like a gaseous version of water in that they can remove substantial quantities of heat by breaking down chemically within the fire. It's a highly endothermic reaction, and there are reports that some of these chemicals also inhibit the chemistry of combustion also. Popular trade names that you might have heard of these types of gases might be FM200, Fe13, NAF-S3. Many are becoming slightly less desirable due to the greenhouse gas contribution that they can make. But these, again, are extinguishing systems. They need to extinguish the fire in order to fulfill their remit. And with these systems, because generally they are fluorinated compounds, if you don't extinguish the fire with these types of chemicals, it can lead to massive production of hydrogen fluoride, which is a very toxic and damaging gas, not something which is highly undesirable. But the design criteria, again, is very simple. For any given compartment volume, fuel, and sealing level of the compartment, you're just looking to get a residual agent concentration of a certain value. So again, very simple design too. And just for future, completion, Halon systems. Halon is the Halon breed of gases were highly revered chemical inhibiting agents, which in terms of efficiency and performance at putting out fires were quite unsurpassed in their capability. They are, of course, now outlawed under the terms of the Montreal Protocol because they're ozone-depleting gases. And it was their cessation that really led to the development of the other type of gaseous systems, which we've just talked about, and also gave birth to really increased interest in the use of Watermist, and prompted a great deal of research into this. Again, the design criteria for Halon was very simple. So what about Watermist? Well, perhaps it's best described as though it's an inert gas system, but in this case, the inert gas is steam, and that must be created by the fire itself. And actually, it's this complexity that makes this different from any other extinguishing system, because how it works, how well it works, and the way in which it works is driven by the fire itself. And not just by the fire itself, but the relationship that the fire has with the enclosure that it's within. And really scale becomes a very important factor here. A big fire in a small compartment might behave very differently to a small fire in a very big compartment. And even during the life cycle of the fire, these properties can change as the fire grows and shrinks. Now, in sealed environments where the fire and geometry allow it, it is most certainly an oxygen removal system, and you can achieve great things where the steam displaces oxygen from the enclosure until combustion can no longer be sustained. It can be an extinguishing system, but this can be very difficult to ensure due to the level of control that you need over the environment and how everything goes. But I'll demonstrate that very clearly to you shortly with some results from some experiments that we conducted to demonstrate these points. It's obviously a very effective gas cooling system. We mentioned before that it was very finely divided droplets delivered universally throughout the compartment. And in that, they can be fantastic at preventing flashover, keeping things cool, and keeping the environment well suppressed. But the design criteria, for the reasons given, are very complicated. And historically, Watermist systems need to be justified really by full-scale and more importantly, accurate testing of a type reasonably similar to the end application. So if anyone sort of asks about, how does it work? Is it by oxygen depletion? Well, sometimes it might be by cooling the fire, perhaps a little fuel removal, if it's specifically designed to control of ignition sources. Again, if that's something desirable, it can be designed in. Deployment of foam. Generally, Watermist systems are not foam enhanced, even though it'd be lovely to do that because, as you'll see, small fires can be quite troublesome for them. But it can be made to work that way if deemed appropriate. And gas cooling, very effective at that. But it can be all or some of these together individually, or even change throughout the lifespan of the fire as it grows and shrinks. And actually, we do see that cycling of fires during Watermist discharge is not a commonplace also, as a large fire can really drive itself to the point of its own destruction, or nearly, but then as it shrinks down, then it starts to generate less steam, and then depending on the ventilation arrangements, it may recover quite considerably also. But another common question, is it like a sprinkler system or a gaseous system? And sometimes all I can say is it's a bit more like one than the other. But again, depends very much on the situation. But the key difference is that the fire and its relationship with the enclosure that drives the extinguishing process. And all these things vary. So I said that I would give you a good example on some of these facets. So here was a very simple series of tests that we did, but they were very well controlled in a 100 cubic meter enclosure, very well sealed rig, but we can adjust the ventilation by removing sections of the door panel, the blue blob on the left there with those dots, those just section door panel. We can operate with different numbers of Watermist nozzles. We could use a range of fire sizes, and we can allow the fire to burn for different periods of time before the Watermist system operates. And hopefully the results from this will show you clearly how counterintuitive some of the operating modes are. So if we look at how long the fire has been burning, how that affects performance, there are two graphs here. On the left, we have the temperature in the enclosure. T0 is when we release the Watermist system. And on the right, we see the oxygen in the compartment itself. There are two oxygen sensors in there. And what we have here is two fires which are identical, ventilation conditions which are identical. The only difference is that we allow a pre-burn time, if you like, a detection time of the fire, to be longer for one fire than the other. And you see that in the solid black line on the left-hand graph. So the consequences for burning for longer is that we see in the left-hand graph that the mean temperature of the enclosure is higher. It's 295 degrees as opposed to 258 degrees. The other consequence of allowing a fire to burn longer is that it's consumed more oxygen from the enclosure before the system operates than a shorter pre-burn time. And at its lowest, you can see the high up in the compartment, it reaches a level of about 8%, just over 8% oxygen, whereas with a 3-minute pre-burn time, it's 10%. And when we activate the system, we see a difference in performance in the time to extinguish that fire. So burning the fire for longer, we extinguish it in 10 seconds, whereas burning it for a shorter period of time, it takes 45 seconds to go out. So I think that's all very logical, but again, counterintuitive. We're rather used to detecting and tackling fires earlier because they're easier. But here's a case where leaving them longer makes them easier for this type of system. Fire size affects performance as well for exactly the same reasons. So here we have two spray fires, a small and large. And again, on the left-hand side, you can see that the temperature, the mean enclosure temperature gets up to about 175 degrees for the large spray fire and only 129 degrees for the small spray fire. Likewise, the oxygen concentration for the large spray fire drops it down to around 15 or 16%, but for the small spray fire to 17 or 18%. And the difference here is not just a change in time, but for this ventilation configuration, it's a difference between extinguishing the fire and not extinguishing the fire. And again, this is a deviation possibly from what we're used to. We're used to systems which do not really behave in a sort of binary fashion. We like that to see a change of performance, but not a major difference, such as whether it gets extinguished or not. Ventilation, another key feature for systems such as this. We can see that they're inherently linked in their ability to put out fires to the oxygen content of the enclosure and how they can drive it down. So here we have, if you can remember the schematic before, where I've removed a series of door panels, 2, 4, 6, and 8. And what that changes between these tests here is not only the temperature of the enclosure, because the fire burns less efficiently. We can see that in the left-hand graph actually, this is more about holding on to heat with the highest temperatures for the least panels removed from here. But you can see, more importantly, on the right-hand graph, it describes how the residual oxygen concentration within the compartment is for the different ventilation levels. And as we remove or increase the ventilation of the compartment, you can see the extinguishing time increase from 14 to 27 to 35 seconds, to the point when 8 panels are being removed, it doesn't extinguish at all. So again, we reach a threshold, and it's a question really of whether we would be able to describe accurately in any design manual when this happens, if extinguishment is an important facet of the overall design. And that's another thing that we need to discuss later on in this talk. People do seem to fixate on extinguishing fires, when actually that might not be what is needed at the end of the day. Watermist density, I mentioned also that we can change the number of nozzles operating within a compartment in this very well-controlled environment. And you can see there as we change from 4 to 6 nozzles on small and large spray fires. Once again, not surprisingly, the more water you put in, the lower you can drive down the oxygen content of the compartment. And the larger fires do that better. We've already seen that. But on a small spray fire, we can see that with 6 nozzles operating, the fire will be extinguished in 52 seconds. But if it comes down to just 4 heads operating, again, we reach a threshold where the fire doesn't extinguish. So hopefully, if you've managed to get your head around that, it is confusing. It demonstrates just how confusing things can be. Fires that have been burning for longer are hotter and have less oxygen available, and may therefore be easier to extinguish. On the other hand, fires which are bigger are hotter, consume more oxygen, and they can generate more steam. And again, they may be more easy to extinguish. Fires with less ventilation cannot replace the oxygen displaced by steam as quickly, and may therefore be easier to extinguish. And fires subjected to more droplets can produce more steam, which may benefit extinguishment also. So now the problem with criteria like this, longer, bigger, less ventilation, more droplets, is these are very difficult things to describe in any given design manual, because they are related between the fire size. A big fire is only big in a compartment in which it looks big. In a much larger compartment, it may be a very small fire. So it's this interplay that makes it very complex indeed. But I think we've probably laboured that point long enough. I just want to show you what this actually looks like in practice. This is some work that we did for the military, and I just want to show you 3 examples. This was for a very specifically designed Watermist system for them. I'm hoping that this will run. This is where it's worked beautifully in rehearsal. But we might be having a little problem now. Sorry about that. I may just have to describe these to you. But basically, in a very large compartment, this was for a marine application. We designed a system for the military, for the warships. And in this case, in the first screen on the first video on the left-hand side, that should have been showing you very nicely how hidden fires, that's under a metal table. These images are taken with thermal imaging cameras. A very large fire in a completely obscured situation. If the fire is large enough and the compartment is well sealed enough, that fire can be successfully tackled because of inerting of the atmosphere and reducing the oxygen to a point where combustion can no longer be sustained. In the middle one, this is a small fire, but in this case, the ventilation of the enclosure is such that small fire will not go out by itself, but this particular Watermist system we enhanced with foam, so that gets taken care of by foam. The one on the right-hand side is slightly more surprising. Again, this is a spray fire onto a hot surface, onto the side of a pump, to simulate a diesel generator catching fire, but with a fuel leak onto it. The surprising thing about this is this fire isn't actually tackled by oxygen depletion. It's too heavily ventilated for that. It's a small fire, it doesn't generate much steam, but in this particular case, the fire only goes out because the object on which the diesel fuel impacts is brought down below the auto ignition temperature of the fuel. So So it's actually about surface cooling and removal of the ignition source. Now again, that's not necessarily native to a Watermist system, and small droplets, they're not actually very good generally at cooling surfaces. But just like the need to deliver foam, this is actually a hybrid system that we produced, which had a combination of small droplets and large droplets. Small droplets to give you all the benefits of intense atmospheric cooling and fantastic steam production, as a standard Watermist system might have, but it also provided large droplets, which were very good for surface cooling and also the delivery of foam to the fire. I'm sorry I couldn't bring you those videos. And I also don't, oh, there we go. Right, so to recap, a very special set of circumstances need to exist for Watermist to extinguish fires effectively, robustly, and reliably, but they are very good at cooling and preventing flashover. Suitability can therefore be very different for different applications, and whether extinguishment is a requirement or not. Now, we need to consider this very carefully. Watermist is seeing a wide range of applications, some more familiar than others, but it's vital that you understand what it seeks to achieve. So I've just roughly categorized these as life safety protection, building regulations compensatory feature, property protection and business resilience endeavors, and that might be of an item which must remain functioning, sort of local application if you like, or of an item where it may be destroyed in the process, but that's okay, but everything else around should stay intact, or protection of a compartment or protection of a building. Now, for each of these, it's imperative to also consider if extinguishment or suppression is appropriate, and if we talk about suppression, how long the system must be effective for. And this is generally a conversation about whether, about who's coming up to help with it. It's the fire service or what the secondary measures are coming to finish off the fire. And also how resilient the system must be to perform. And having considered all those factors, whether the application plays to the strengths of Watermist, and we'll talk about those in a moment, and whether Watermist is the best option for the application itself. Now, I think hopefully you've started to get a good handle on what the strengths are of Watermist. Very good on high heat output fuels, and particularly liquid fuels, hot environments, enclosed environments. This optimizes steam production and containment of that steam for displacement of oxygen as well. Best for small compartments with low ceiling heights. Now, the reason more for this is because that can also maintain the momentum of the droplets themselves. Around a fire, there are a lot of repelling forces to drive droplets away, and Watermist systems overcome this by generally injecting them in a fairly fast and furious fashion so that they can overcome these repulsive forces. Certainly a strength is direct application, very good environmental cooling, and they can be good on hidden fires if the fire is large enough and the compartment small enough in relation to each other to globally reduce oxygen content, and they're very good at gas cooling. The weaknesses, ventilated spaces, as hopefully we've demonstrated there. You can cross a threshold so that a lot of the benefit disappears all too quickly. High ceiling heights, we said before, where the momentum of the droplets gets lost with distance. Small fires can remain remarkably resilient against Watermist fires, against Watermist systems, because they don't have the energy to drive the circumstances for their own demise. They're not necessarily very good at cooling hot surfaces, not necessarily very good on deep-seated fires in Class A type fuels, which, again, as we know with sprinkler systems, might require wetting the fuels. Hidden fires, if small. Another thing to consider is that once the water supply to a Watermist system is exhausted, there can be little benefit thereafter, because so very small quantity of water have actually been put down. And their weakness is really trying to assure extinguishment can be quite a challenge. And we'll keep revisiting that. But that said, for life safety purposes, we've seen some very good implementations. We know that they have the facet of exhibiting excellent atmospheric cooling, very good for flashover prevention, and really preventing fire growth in small domestic residences. An aid to timely detection and evacuation, and generally these are specified without an expectation or requirement for property protection, and as extinguishment is not required. It's more about getting people out of the building, and they can do that very effectively indeed. And obviously post-Grenfell, they've been proposed as a good measure for assisting the escape of occupants who can be quite remote high up in high-rise buildings, and we've seen some good examples on where that certainly is a feature. Now, building regulations compensatory features. This is where the building regulations can't necessarily be applied in full, so other measures are made to compensate. And these may be things like extended travel distances, limited escape routes, just single stairwell, lack of passive protection, very topical at the moment, oversized compartments or over-occupied compartments. And I think decisions as to whether Watermist is appropriate here really depends very much on considering each of those in turn for appropriateness, given the strengths and weaknesses of what we've already discussed. But I won't dwell on those. It's a very complex area in its own right. Now, in terms of property protection, for local application property protection, that is protecting an item of equipment, Watermist is often the very best option. In some marine and high-risk environments, it's a good option too. And the reason there is quite obvious. In the marine environment, we have very well-sealed compartments. The fuels that they use generally lead to very large instantaneous fires, and it all plays to the strengths of Watermist, as we've seen as being very effective. The grey area, I would say, comes to when we look at commercial business and property volume protection. These are really the domain where sprinklers are used, warehouse storage, and the like. And this is where we see most challenges, and often we see them putting in facilities where really sprinklers would have been a better choice after all. And I'll go on to some of the reasons for that later on. But certainly they can also be considered as a practical alternative to where gaseous systems might be deployed. They can be a very good option, subject to the fires being of the right type to play to its strengths. So I won't dwell in this, but building regulations do talk about water systems, generally in terms of sprinkler systems, as we said before. They can be used to compensate in various codes, to reduce the fire growth rate, allow larger travel distances, larger compartments, reduce fire resistance periods, etc., etc. And also, but where they have been mentioned, and this is a phrase out of BS 9999, it says where it is proposed to modify the risk profile by using a fire suppression system other than a sprinkler system, it will need to be demonstrated that this system achieves the equivalent standard of fire protection and reliability. Now, the fire protection bit is quite easy to generally demonstrate in the laboratory. You can tweak and play with any system to make it good. But reliability is a very different thing altogether, and that is generally earned through really kind of over the years of refining, tweaking to increase the, really development of pedigree, I suppose, of a system. But if we hold on to that thought, we probably need to consider what makes things reliable. Now, I don't want to enter into an all sort of sprinkler versus Watermist debate, but it's sort of inevitable in some respects to visit here. It's a good benchmark because sprinklers probably are the most reliable suppression system that we have. And generally, when asked to operate within the figures, most analysis show them to be over 90%, 96% likely to function properly when called upon to do so, which is an enviable figure which no other type of suppression system comes close to. But it's, in the early days, sprinklers weren't perfect either, but most problems have now been resolved by specifications for equipment, specified clearances between moving valve parts. It's often a criticism that sprinkler systems look like Victorian architecture, but it's with good reason. That actually brings in resilience into their whole operation. Size limits, minimum size limits on various orifice, and that overcomes a lot of the water quality problems that we have. But 8 millimeters, these are quite large orifice sizes. Continuous refinement of how we design systems and install them. And certainly RISCAuthority alone spends hundreds of thousands of pounds trying to refine our rules to maintain this level of reliability of the systems. They have good specifications of how to design against a range of hazards, and water supplies are very secure, reliable, and incorporate duplication also. There's also testing and certification of hardware, certification of installing companies. There's auditing of the installing companies through things like the LPS 1048 schemes and FIRAS schemes. There's also rigorous inspection and testing of the installed systems by way of acceptance tests, flow tests. There are weekly tests done. Pumps are run up each week as well. And there's checking of installation and control valve function. So as you can see, it's an all-through life solution that has been required to produce reliability within sprinkler systems. But even then, we still find problems, albeit rarely, but it does take a lot to achieve these levels of security. I just want to do a few side-by-side comparisons. Probably one of the primary differences between sprinkler and water mist systems is actually the extent of protection. When I'm confronted with people saying I don't know whether to put in a sprinkler system or water mist system, it's more than just talking about the technology and the methods with which it puts out fires. In specifying a sprinkler system, you are signing up to a list of rules that tells you every area of the building that has to be protected. And it's even the hidden areas, the voids, the cavities, if they contain combustible things. It is basically a total building protection system that is being signed up to, not just the fact that you're using a nozzle that puts out big drops. But when you specify a water mist system, it really is for compartment protection, and generally it's down to the user to determine what areas, what subcompartments of that building should be protected. So there is a key difference there. With a sprinkler system, if you see a sprinkler system in a building, you'll know that if there are voids with combustible, voids over a certain size with combustible content, the sprinkler system will be running in those invisible places too. The same is not inherently encompassed in water mist design by default. And when you look at the hardware that's used as well, I mentioned Victorian architecture on the left-hand side. That's a cutaway of a sprinkler control valve, a large flap that lifts away, really generally revealing a hole around 4 inches in size for the water to get through. But water mist systems, they require much lower quantities of water, but dependent on much smaller orifice type equipment than solenoid valves, which have a much higher failure rate than sprinkler alarm valves. There's also looking at orifice sizes themselves. We mentioned the minimum orifice size for sprinkler systems, around 8 millimeters, and as such, they get tested every 25 years, and the products are interchangeable. If your system is your heads need replacing, you can go to any number of manufacturers and put their head in place of it. Water mist nozzles, very much smaller orifice sizes, and we know in our laboratory, even with trying to be fastidiously clean with our water, we do get issues occasionally, and as such, these need testing every 3 years, and they're not interchangeable between systems. You do need to go back to the original OEM provider for nozzles if more are required. Testing of water supplies is also a difference. Sprinkler systems are designed so that we can test the water supplies, and they are tested regularly, and with water mist systems, we find sometimes that's just not possible. Duration of water supplies. Obviously, for a sprinkler system, it's defined by the hazard, but 60 minutes, 90 minutes, and even 120 minutes are not out of the question. And even after that water gets exhausted, were it ever to, the amount of water that's gone down can still have a controlling effect on the fire. In water mist systems, the durations are generally very much smaller. They may be defined by a standard, but often by the installer themselves or the manufacturer themselves, determined through testing. but obviously in putting so little water down, once the system generally finishes firing, there can be little residual protection of that space thereafter if nothing else has come along to intervene. And then finally, water application rate. We've got it specified against hazard for a sprinkler system, and I think, as I've already described, it's really dependent on the system itself for Watermist, as a few equivalent type test procedures apply. So, sorry, in that slight whirlwind, I hope it wasn't too confusing, look at what makes reliability informants. Currently there's little by way of codes or standards to dictate the Watermist systems will have many of the features that we know make sprinkler systems effective for the long-term protection of property and business. And we do have, I have seen justifications of Watermist systems which have basically said that, sprinkler systems basically have a tank, a pump, lots of pipe work and the nozzles, and they're 96% effective. Our Watermist system essentially is made up of a tank, a pump, some pipe work and some nozzles. So we can infer the same level of reliability. Totally wrong, but I do see it written down occasionally. So what's RISCAuthority and FPA done about this? Insurers, and many of you are listening in, I'm sure, sought some guidance as to how we could help while there is a lack of guidance out there. RISCAuthority does have a remit to promote new technologies where they can provide most benefit for business and property protection, and we like to see it go into the right places where it's actually the best option. And what we've produced are a suite of questionnaires which hopefully will allow designers and specifiers the freedoms to really demonstrate to the end user why this is the best technology to use at any given time. These are freely downloadable from the RISCAuthority website. There are 3 of them to cater for the 3 types of Watermist system that we see being installed. IQ1 is the Watermist questionnaire for building compartment deluge systems. So that's the use of open head nozzles used to protect compartments in the same way that a gaseous system might be used. These are typically things that we see in some factory environments, but certainly greatly in the marine environment. IQ2, a Watermist questionnaire for local application systems, protecting of deep fat fryers, cooking equipment, can be very effective there. And IQ3 is a special one. This is a Watermist questionnaire for building compartment systems which use closed head systems. These are things with bulbs in them. And there's some very good reasons, which I'll explain very shortly, as to why we think that's important. Why have we done questionnaires and not produced guides or installation rules? Well, Watermist function is complex, as you've seen, and there are fewer standards than there are for sprinklers existing to rely on for their installation. And really, I hope you've seen the science is quite complex here, and to describe for every eventuality is almost impossible. But what the questionnaires do is they check that all the design elements have been considered, that the usual risk control logic has been followed, properly recorded, and is owned by someone. And we felt that was the only practical approach to go to. Now, based on some of the things that we've seen when we've been doing forensic examination of failures of all types of suppression systems, not just Watermist, the first and key one is that design intention is not properly understood. Be it about whether it's a relationship between whether it's to do with property protection or life safety, we do see things more fundamental in that, an assumption that the system would extinguish the fire, but actually it didn't, and it wasn't associated with an alarm system. So not only did it not extinguish the fire, it also didn't raise an alarm that there was a fire, and then the building carries on to burn down anyway. These are quite fundamental issues. The risk never properly investigated or understood properly. We see an inappropriate use of systems to apply to different applications. System design never validated against an appropriate risk. We've been through a period where we see a lot of onshore water mist applications being justified by experiments conducted for the marine environments, which use very different fuels, and obviously the enclosure details are very different also. And you need to question whether that is appropriate or not. Also, a key one is that the system design doesn't necessarily consider all modes of operation of the equipment it's protecting. And we've seen some very large losses where the system probably would have worked fine had the equipment been configured as it's normally configured. But then fires don't generally manifest when things are normal. Fires happen when abnormal stuff happens, and maybe if a fryer hood has been lifted or something, then the system fails to operate because the ventilation details have now changed. Now these are basic sort of risk analysis faults, which are inexcusable for any type of suppression system, not just water mist. We see very short water supply durations being used, and some of these we found to be shorter really than the shutdown and times of associated equipment and control of ignition sources. So we have seen water supplies being short on the time it takes for surfaces to cool down before the auto-ignition temperature of the fuel. We also see systems which are not interlocked with power, fuel, ignition sources, ventilation and conveyancing equipment. We've seen detection that is too slow for the type of system it is, insufficient control of ventilation, and insufficient guidance, inappropriate referencing of sprinkler equivalency, and as I mentioned before, assumed level of sprinkler reliability, and no overall ownership. Now, I know that's a bit of a gripe page, but I thought I'd distill it all into one. But where I do have a concern is when it comes to very large area systems with large array of heads, which are closed heads, and they are actuated by the popping of a sprinkler bulb. Now, it may not be known to many people, but sprinkler systems are deliberately designed not to cool the ceiling gas layer, because that is the only means with which it's the temperature at the ceiling is the only means with which the sprinkler head can communicate with the size of the fire below. So if the next sprinkler head in an array to go off needs to understand what temperature the fire is and whether that bulb is needed. So the heads are very large, so they don't cool the gas layer. And and a great deal of effort goes into sprinkler design to ensuring that is always the case. However, one of the concerns we have as FPA is that in the water mist arena, commercial protection standards have been written, which use the same bulb standards and the like, but these are, we mustn't forget, these are very small droplets, and these are essentially gas cooling systems, and we don't believe that sufficient work has been done to consider whether one head activating can then impair the ability of the next head to operate, even though it's required due to cooling of the gas at this height. So we currently feel that the commercial water mist installation standards for systems of this type should be treated with great caution. So in summary, just really to close out, water mist can be the best protection option for many applications, but not all. It is imperative to fully understand all performance factors pertinent to meeting the design requirements and assessing whether the technology, what it can achieve, is better than all others. In the use of the questionnaires, it only asks details. It only asks questions that should be answerable by anyone competent to design and install a system. And really, if people are struggling to justify the system or to complete the questionnaire, that should serve as a warning to you. That's all the grounds. It isn't simple. You do need to do the detail or be convinced that the details has been done by others. So I said, I promised I'd leave you with a few rules of thumb, and these may be slightly controversial, but here we go. I'd probably sum up by saying that water mist can be a good option for flashover prevention as a component of life safety provision, and there are some very good domestic and residential applications for water mist, without a doubt. It can be an excellent local application system for industrial and kitchen type risks. It can be an excellent alternative to gaseous systems where enclosure integrity can be assured and fires are likely to be large. Where extinguishment of the fire is a requirement, the total design solutions to assure this, we know, can be complex, expensive, and may lack resilience unless specifically designed for. And I guess this is the large area that we see competition happening between sprinklers and water mist systems. And really, when you do start to actually fulfill the requirements of building regulations and seek not only equivalency in terms of performance, but resilience, we can very quickly see that any perceived cost saving can quickly get gobbled up to do while trying to do the full and proper job. In property protection applications, FPA questions the use of closed head nozzles where more than one or two are required to protect the compartment. So in small compartments, where you may only have one or two heads which might be bulbed, such as a domestic and residential or hotel type environment, it's probably fine. But to protect large open floor areas with bulb systems, we still think there is more work to be done there before that can be before that would be advised. And finally, really, when asked whether it's a sprinkler-like or gas-like, to be on the safe side, assume it's gas-like in that it requires a well-sealed enclosure and control of ventilation, but assume that it's sprinkler-like and that it must have direct access to the fire, and really assume that where the water doesn't go, the fire won't go out, unless someone can convince you otherwise. Now, I think we've taken the best part of an hour to go through that. I hope it was understandable by everyone, and the slides will be made available on the RISCAuthority website. Now, I do see I have a few questions here. If you just forgive me a little, I will just try to have a look. I think I've been sent one email. I'm afraid we are all working from home, so let me just have a look on questions. Oh, I think this is where I will lose the audience if I don't work this out quickly. What is the maximum open space enclosure that the mist system is suitable for? Well, that's a very good question indeed, and I hope I've probably demonstrated during this webinar that it's a very difficult one to answer. For a very large fire, it can be a very large enclosure. I do apologize, but that's a difficult question to answer straight off. I hope you can see that that is why often we need to have large-scale testing to determine exactly those things. Or computational fluid dynamics is used increasingly within the marine environment for this. I've got another question here. It says, are these results on high pressure or low pressure water mist? In the case of the graphs that I showed you, they were produced using a low pressure water mist system, or let me call it a medium. It was about 14 bar system. That was a question that came in. Another question, sprinkler systems prevent fire spread until the fire brigade arrive. Is the expectation of the mist system to do the same, or is it designed to extinguish? Well, that goes back to what the core requirements are of the system. Whilst it's well understood within the sprinkler fraternity of what a sprinkler system must do, it is clearly a suppression system. For a water mist system, it is something that needs to form part of the overall fire management plan. And if it is in a domestic and residential environment, then typically it is to afford people time for egress and evacuation and not extinguish. And the water supplies will need to be selected accordingly. Even in other environments where it's expected to extinguish, well, that's a very specific design criteria, and you will need to consider what happens if that isn't, if that can't happen. Let me just see what other will British standards be updated to make specific reference for water mist. There are new British standards for water mist. I've referred to one which is a commercial standard. There are more for domestic and residential, and some laboratory testing that they're taken through as well to assure compliance. And I have another question of What about evaporative cooling from sprinklers at ceiling, preventing or delaying response of adjacent sprinkler bulbs? That's a good question. So I think that question is referring to can sprinkler systems be subject to head skipping as well? The answer is they can, but due to the nature of the discharge and the large drops, the efficiency of heat and mass transfer between a gas layer in the sprinkler system and the sprinkler droplets themselves is very much less efficient. So it is much less likely to happen. And the rigs built to determine this were built by the insurers many, many years ago at RAF Cardington, and it was an enormous rig, some 80 meters down each side, and head skipping trials were done to really evaluate what the properties of the sprinkler head needs to be and the distances between them to minimize the impact of head skipping. Another question. Enough people still seem to be hanging on. We still have over 300 people attending this, as I say so. Another question, can you talk a little about representative fire tests and how much interpolation you see where tests are not fully representative of the final application? Now, that's a very good question. Certainly, the key factors that I would look for in assessing whether fire testing is appropriate to your particular end application, ceiling height is a crucial factor, and compartment volume is a crucial factor, and ventilation is a crucial factor also. And if I then extend that to also say that really the heat release rate of the fuel and fire size are contributing also, I've probably defined all the variables that basically say testing needs to be fairly bespoke. But I think probably it's a time to take quite specialist advice. The larger the compartment size, probably the further away you get from having an assurance that tests are relative. I think typically what's the methods which have been used in the past, and certainly with the marine environment, is that you can test at a scale and then you are certificated for any compartment size smaller than that, but not larger than that. But that may have been relaxed slightly in recent times. I will need to check up on that. There's a question of, are we moving towards a British standard? Well, there is now a British standard for commercial systems, but for the reasons I suggest, we treat it with some caution for bulbed closed head systems. I think the problem that we have with development of standards is that now you can hold a sprinkler standard in one hand and a Watermist standard in the other, and assume equivalency just on the basis of the documents being in existence. But as I said, there are things in harmony with things like the FPA rules for automatic sprinkler protection. Sprinkler systems, inherent in the name, is a lot more specifically to do with area of coverage. So some of these questions are very long, so if you excuse me, I will probably answer those personally to you. I'll answer one more actually, because it's probably topical to the audience that I see we have here for the residential environment. It's, can I ask your thoughts regarding modular systems for residential high-rise premises, as ADB both focuses on BS 9251? Now that is BS 9251 is a residential sprinkler standard. Actually, it's quite limited in height, not necessarily meant for the height of buildings that we commonly see it being installed into. It is what I would call quite a loose standard, in that it is probably only about 20% sprinkler design. The other 80% of decisions need to be made by a fire engineer. So anything vaguely complex, it basically refers you across to looking for additional help from others. However, I think the crucial thing here is to think about the protection that you're trying to afford and what you're trying to achieve at the end of the day. The starting point, particularly in a high-rise environment, is suppression systems are not a method for making up for poor building fabric and poor passive protection, which is missing or non-existent. I would argue that's probably a little more like putting lipstick on a pig. Any suppression system needs to have a good and appropriate passive envelope to perform within. So correcting the passive envelope is the starting point for all suppression system installations. In respect of high-rise buildings and water mist systems, if it is to assist with evacuation, they can be very effective in doing that. As I said, they're very effective at cooling and keeping temperatures low and stopping fire spread. If they are looking for a property protection element, because there are some requirements in high-rise buildings to maintain the structural integrity of the building itself, well, that is a different type of system altogether, and even the BS 9251 system would be inappropriate for achieving that. So there certainly is an application in the high-rise environment. I think a lot of the problems which we have seen in that environment for both sprinkler systems and water mist systems, we have been around to investigate some, but generally to do with the quality of the installation itself. And having worked so hard to build up the reputation of sprinklers, it would really be a great shame if that gets destroyed through poor implementation and perhaps just changing one problem for another, a fire problem for an escape of water problem. So I think I will, actually I've got one more question which is coming. If used in a commercial kitchen, can the water mist heads be blocked by grease in the same way that fire suppression heads can be, and can they require a plastic cap? There is a very good new standard produced or certification scheme by BAFE for kitchen suppression systems, which I hope will take care of some of these issues to increase the likelihood of systems to operate in this sort of environment. Protection of the heads is obviously quite fundamental, particularly in the dirty environment of a greasy kitchen ducting network. But again, that is a nice case where the ability of the system to perform has dependencies on many other things. Interlocks with the gas supply, the ventilation, or the electrical supply to the heating equipment. It is also the ability to perform in that environment is also inherently linked with the duct cleaning regimes and how well that is done, and that is all compliant also. So it's a complex area with a lot of additional requirements. I'm probably going to end it there because I'm probably babbling now. Anyone else, I see there are some more questions, but if you don't mind, I will answer those personally. I hope it's been informative, and thank you very much for tuning in. I think we've had a record-breaking number of people attending this seminar, well over 300 at one stage. Thank you very much for listening in.